Hi, I'm Xuanyu Wang. I'm a joint PhD student at Xianzhou University and City University of Hong Kong. I'm glad to share our paper Predict and Drive Avatar Motion Adaption in Room-Scale Augmented Reality Telepresence with Heterogeneous Spaces. This work was done with Dr. Hui Ye, Professor Christian Sandor, Professor Weizhan Zhang, and Professor Hongbo Fu. Augmented reality telepresence has emerged with the ability to empower users located in different remote spaces to interact with each other in 3D, giving users the illusion of human teleportation. The emerging AR head-mounted displays such as Microsoft HoloLens facilitate the development of AR telepresence systems leveraging volumetric capturing or avatar-mediated techniques. While the volumetric capturing approach can be very expensive, most commercial applications choose to represent humans as avatars, such as the Horizon Workrooms by Meta and the Microsoft Mesh app for HoloLens. However, simply copying a user's motion to his or her avatar in another space could easily lead to anomalies, such as the avatar penetrating obstacles and interacting with air. To tackle this problem, researchers propose to generate and use a mutual movable space or retarget the avatar's position at the beginning or constantly during the whole experience. However, these methods limit the telepresence experience in a small sub-area space, fix the positions of users and avatars, or fail to present smooth avatar transitions. Moreover, finding the semantically correspondence position can cause a delay between the avatar retargeting and users' real transitions, which might break the semantic synchronization between the user's verbal conversation and perceived avatar motion. So, focusing on the avatar transition delay, in our paper, we first examine the impact of the transition delay and explore the preferred transition style with the existence of such delay through two pilot user studies. And then, with the results showing a significant negative effect of avatar transition delay and providing the design choice of the transition style, we propose a predict and drive controller to diminish the delay and present the smooth transition of the telepresence avatar. We also evaluate the effectiveness of our proposed method through a user study and visual comparisons. Next, let me introduce our work step by step. Our first pilot study aims to answer the research question that how do the existence of the transition delay and the lack of a transition process on the avatar affect the user's perception of its locomotion? We set two delay telepresence scenarios for the user study, both with real-time verbal communications and transitions from one place to another. To illustrate them, we sketched the remote space on the left and the local experiment space on the right to show the things happening in the two spaces. The TVs and whiteboards in the two spaces are connected through Internet of Things. Scenario 1 happens in the dining room. The local user just finished the dinner with the remote user through telepresence. The remote user asks the local user, "How was the dinner?" The local user answers, "It was nice." Then the remote user asks, "How about we watch some show?" The local user answers, "Okay, let's do it." The remote user says, "Let's go." And then the user in the remote space immediately starts walking to the living room. When arriving at the sofa in the remote space, the remote user says, "Let me turn on the TV," and turns on the TVs in the two spaces. With the remote user being visible, the local user would perceive the above actions of talking and turning on the TV to be initiated by the avatar and observe the avatar's transition from the dining room to the sofa. In scenario 2, the local user is looking at a whiteboard while the avatar is in the dining room. The user wants to call the remote user to see the whiteboard, shouting at the avatar, "Hey, come check this board." The remote user hears and answers, "Okay, I'm coming," and immediately starts walking from the dining room to the whiteboard in the remote space. When arriving, the remote user says, "All right, show me." Similarly, the user observes the avatar's transition. We recruited 16 participants. We pre-recorded the avatar speech and path and reconstructed a rough virtual replica of their experiment space, as shown in the figures below. On the left is the participant's view, on the right is a bird view of the space. We used a simple but interactive mobile AR-based manual create and align approach to achieve this rough scene understanding and annotation. Regarding the combination of transition delay, transition process, delay style, and obstacle avoidance, we have 4 study cases: flash and idle, flash and walk in place, walk and void, and walk and no void. Repeating in 2 scenarios makes 8 tasks for each participant. After each task, we ask the participants to fill in a 7-point Likert scale on the content's similarity to the anticipation, semantic rightness, and their overall preference. The videos show the case in scenarios 1 and 2 respectively. The conversation part is skipped in these videos. In the flash and walk in place case, the avatar transition is delayed for 8 seconds, and while being delayed, it performs a walk in place locomotion. It flashes to the target position when the remote user actually arrives at the remote target. You can observe the TV being turned on as described earlier. In the flash and idle case, the avatar is delayed for 8 seconds and flashes to the target position while being delayed. It stands still. In the walk and avoid case, the avatar is not delayed and walks to the target position while avoiding obstacles. In the walk and no avoid case, the avatar is not delayed and walks to the target position while not avoiding obstacles. We conducted H-test and post-hoc Dunce test on the data combined from the two scenarios. Here are some key conclusions. First, the maximum delay and the resulting lack of a transition process significantly harm the user's experience, even more than the avatar's penetration of obstacles. Therefore, it is necessary to diminish the delay and present a smooth transition. Second, walk in place has higher mean scores than idle. Though not significantly better, it has certain indication of movement. And finally, steering the avatar to avoid obstacles is still necessary in AR telepresence. To diminish the delay, we need to predict the user's target as early as possible. But accurate real-time target prediction with zero delay is hard to achieve in most of the time, which leads to our second research question that what would be the best transition style for the avatar when there exists a relatively small delay before the exact target of the remote user can be predicted? To answer this question, we conducted our second pilot study. We recruited 12 participants with the same setup as study 1. We considered 3 transition styles, namely const, speed, and hybrid. Repeating in 2 scenarios makes 6 tasks for each participant. In this study, the avatar is delayed for 4 seconds in all the tasks. In the speed case, the avatar speeds up the walking to arrive to the target position simultaneously with the remote user. In the hybrid case, the avatar did not speed up but flashed to the target position when the remote user gets to the target, also achieving a simultaneous arrival. In the const case, the avatar did not speed up in the whole process, walking to the target at a constant speed. As a result, it arrives with a 4-second delay. After analyzing the data combined from the 2 scenarios, we found that in the presence of delay, speed is significantly better than hybrid and const in preserving the semantics of the interaction and is significantly more preferred. It can reduce the transition delay and present a smooth transition process. We will implement this transition style in our prototype. To sum up, from study 1, we learned that we need to predict the user's target in advance to reduce the transition delay. And we need to generate a path that is safe and natural enough for the avatar to move to the target position. From study 2, we obtain the design choice to speed up the avatar's transition when there exists an inevitable prediction delay. It helps keep the semantics of the conversation context and the avatar's motion synchronized while maintaining the coherence of the transition process. With this in mind, we introduce our predict and drive avatar motion controller. It has a target prediction component and an avatar control component. The target prediction component is based on the spatial-temporal relation between the user's moving direction and the object slices, as shown in a simple illustration. Specifically, we calculate all the object slices from the visibility polygon of the space and define an object as a target if the user's moving direction stays in the object slice for a certain period of time, half-second in our implementation. However, for the situation where there exists an obstacle between the user's starting point and the target point, as in this video and the figure on the right, it will have a relatively big delay caused by the semantic ambiguity of the locomotion. The target is cleared only in the latter part of the transition, as in the orange arrow. So, to reduce the prediction delay caused by such ambiguity, we further design a grouping component as an upgrade to the basic approach, as shown in the middle video. It calculates a virtual target by grouping the objects the user is approaching instantly at the start of the transition and updated every frame with 0 delay, which will consistently approach and eventually reach to the real target. The detailed formulation and implementation can be found in our paper. We implement our avatar control component based on the artificial potential field method. The controller maintains an APF of the space as shown on the right and determines the avatar's moving direction using the negative gradient of the APF. We adjust the avatar's speed to ensure semantically simultaneous arrival. The formulation is illustrated in the supplemental document. After developing the prototype, we conduct an initial evaluation. We recruited 12 participants with the same setup as studies 1 and 2. We compare the ground truth trajectory GT, the path generated by our basic approach, and the path generated by our upgraded approach with dynamic grouping. The paths are shown in the figure in green, orange, and blue, respectively. GT is the trajectory recorded from a real human, representing the most natural avatar path adapted from the remote user's transition. Basic is the transition generated by our basic method. It has a start delay because it needs some time to determine the target with the existence of the obstacle, while the transition generated by our upgraded method with dynamic grouping has 0 delay. After analyzing the data, we found that grouping provides a decent experience with no significant difference to GT. For more detailed discussion and visual comparisons, please refer to our paper and supplemental video. So, in conclusion, we explore the avatar transition delay and the transition style with 2 pilot user studies, proposed a predicting drive controller to deal with the delay and present a smooth transition of the Telepresence avatar, and conducted initial evaluations to show the effectiveness of our proposed method. Future work can be done from improving the generalization using more advanced target prediction methods, exploring more detailed short-term motions, and addressing scenarios with multiple users and spaces. If you have any questions, please feel free to contact us. Thanks for watching.